control the shell temperature, antenna base shell temperature between 22 degrees to 28 degrees. We have AC plants over there. So if goes beyond 28 degree, antenna will stop working. It alarms first. When it alarms, starts alarm at after 28 degree, it will wait up to reach up to 30-31 degree, and after 30-31 degree, antenna will stop its working, and it shuts down all the systems there. Mesh material is a stainless steel. It's a mesh is a stainless steel material. Where? Hmm. Huh. We have AC installed at antenna base line. You can see this tower is there, concrete tower. That tower is inside that there is a system again. So that ACs are there, some electronics are there, some safety, all these control and sentinel systems are there. Servo racks are in place, telemetry racks are in place. Also electricity and all ACs are also there. So everything is inside that concrete tower. And it is shielded. That concrete tower contains a mesh, Faraday cage, that is surrounded by, so that internal and external interferences can be avoided. High wind is again a critical parameter. So if wind speed goes high, there it's a limit of 45 kilometer per hour. It waits for some manual intervention. If nothing happens, it waits for 10 minutes maximum, and then antenna decides to park itself. Then the electrical power is also we have to monitor, because most of the time it's in rural area, so there are most of the time power shutdowns are in place. So we have to monitor this. We have electrical backup as well, our own. We have provided diesel generators for that and UPS power as well, but we have limitations on that. So it is useful parameter to monitor whether we are running on genset or electrical power supply from electricity board. So intruder alarm is again an important parameter used here. Panic alarm. Panic alarm is provided because people are going there at antenna, which is at remote place, and people are working. Sometimes they are not feeling healthy, so they may encounter some animals there. So wild animals are also there. Some snakes will be there. So as this is very remote, we have to take care of this. And if they found something that is emergency, so they can press that panic alarms and call the control room line, so that action can be taken and support can be provided to them.
These are all fenced or something?
Intruder is it's a abrupt change. Matlab something is automatically abruptly is going to happen there, so that is taking action itself. So these are again I talked earlier about this critical and less critical parameter. So temperature, smoke, fire, high wind, these are panic alarms are critical, and if power failure is there, it's okay. So we can run on genset and UPS, but we have to act on that after certain limit. So there is no as such rush. Okay. And intruder is again less critical. So mostly control room action can be taken on less critical parameters, and on critical parameters antenna acts on itself. So this is the critical parameter block diagram, how it is working. So we have LM35, sorry. We have LM35 temperature sensor to monitor temperature and smoke and fire detectors in place, which communicates to the signal analyzer. And this signal analyzer is again provided with TCP/IP to communicate with control room via optical fiber, and it is again provided with local alarm at antenna. So that again buzzers up if something goes wrong. So that signal analyzer is connected to the driver via solid state relay, which acts on electrical power distribution mode, which can stop antennas working. The next, this is the block diagram for less critical parameters. This is control. Motion sensors are in place, magnetic door sensors are there. So if doors get open or it keeps open by some accident or by mistake, it monitors that. So motion sensing infrared sensors are there. So that are again fed up to the signal analyzer, communicated to the control room via optical fiber, local alarm. It again takes the inputs from three-phase from electricity power. Then camera is there and diesel generator. These are again important to monitor the electrical things. Camera is in place because we have to monitor the antenna safety. So that is provided there, whether who is going in, going out. Then motion sensors are there again. Then basic sensors used are, these are the basic sensors used, like solid state relay, then smoke detector, magnetic door sensors. This is the alarm, buzzer, and this is IR sensor. This is the circuitry we have used for monitoring this Sentinel system. So we are taking inputs from high wind from wind meters, then temperature monitoring, PIRs, then smoke and do the power generator say then set is there, planning buttons. All these inputs are placed on that card, and that is connected to the control room. So this is how the antenna shell Sentinel system is implemented. So I'll start with A. A is the electronics rack. So these are the electronics rack. Then B is the telemetry system rack. C is the signal analyzer. It takes the input from temperature D, E, and F. Then acts depending upon the action. Signal moves to G, and again it is sent to control room with alarm detection. Then smoke detector is mentioned by H, and receiver electronics rack is I. And this whole concrete tower is covered by Faraday cage. Also, this blue square is a insulation wall. So thermo insulation is also provided there. So if you go inside, there is a very low temperature, around 18 to 20. So as I mentioned earlier. So this is a basic in general, electronics sentinel monitoring tool where we are observing and monitoring these parameters from electrical system. We can monitor the temperatures at various labs from main building. And these are antenna-wise status for electricity, temperature, smoke, whether ABC link is on, whether communication is on or off, and whether it is communicating properly or not. That has to be synced with this time. So Sentinel system for high lift platform vehicles. So these are the high lift platform vehicle you can see at in front of antenna. People can go up there in the right focus on the antenna. So there are prime electronic circuitry with whatever radio frequency is reflected from these which are collected there, right focus and then sent to the down to the electronic side, the base, and then it is sent to the main electronics building at via optical fiber. So this is used for remote site working. People have to go there, fix their jobs and come down again. So that is very important and crucial thing while maintaining the antennas. So we have used IoT based Sentinel system for this, and it contains the protected doors, unauthorized entry to the cabin of the vehicle. Then fire and smoke inside the cabin, vibration sensors are on, and it is protected with the battery. So again there is some signal circuitry is there installed so that you can protect the battery.
What is IoT?
Sorry?
What is IoT?
IoT is Internet of Things. We are using the internet to get this signal analyzed and transfer the messages. It's a cloud control over the internet. We can control and monitor from anywhere actually. So that card is there and it sends and acts. Protected it, sorry?
Protected the battery. What does it?
If someone's these vehicles, suppose some people go at the antenna for doing their maintenance work, fixing up jobs, and somehow they couldn't able to complete at the end of day. So they can't get the vehicle back. They have to leave that vehicle over there because that vehicle is big, and considering the traffic and road situations, it is not that much worthy to go next day again. So people leave that vehicle over there, and that's why we have designed this Sentinel system for this vehicle. So it controls and monitors everything for that vehicle. So surrounding environment can also be monitored by cameras. There are cameras installed, passive infrared sensors are there. Then spare wheel. Because it is a remote place, people tries to steal, theft, that we have to protect actually. I am coming to that. So it is equipped with GPS again. So if someone tries to steal the vehicle, whole vehicle, then it has a GPS installed within it. Then audio alarms are there also. Suppose there are 3-4 homes nearby. So vehicle can shout, and people are surrounding, living there, can wake up with this, whether what is going to be there. Next. This is a block diagram actually. So this is the master control unit. It is provided with wireless modem which connects to the internet cloud and sends the SMS, then messages to the data servers and even your laptop if it is configured. So we have 4-5 entries configured for this. Some numbers are there, so that numbers get messages from if something is going to be happen. So door sensors are there, wind sensors, battery sensors, variable sensors. It's spelling mistake, sorry. Then vibration sensor. ER sensors are there, smoke sensors are there. So this whole unit communicates via wireless modem to the internet cloud and it sends the messages. If someone tries to steal the vehicle, someone removes the battery, wheels are being removed, or any suspectable entries are detected by infrared sensors, then it gives the alarm and messages will be sent to the registered numbers. Yes.
Because this vehicle is controlled by totally by internet.
Yeah.
Suppose I have a vehicle near some antenna,
Yeah.
and the antenna is working. Then won't this internet affect the signals which we receive in the antenna, or interfere with our like signals?
At some level, yes, because we are again dealing with the radio frequencies, and these are again the GPS signals which are in the band of 900 to 1100. So this will affect to some extent, and also we from 850 to 930 some GPS signals and that mobile signals are already affecting us. So this will be not that much affecting because that band anyway we are almost putting as a flag data for astronomical uses. Got your next is the protocol. So engineers and technicians will have vehicle accompanied with a driver during daytime and security with proper lighting aids is provided during the late hours. If some engineers and technicians will go late night, they have emergency work, so this will be helpful for them. First aid kit is always there with the vehicle. Doctors and hospital numbers are also provided with the vehicle, dashboards, and even with drivers also. Then availability of local resident security persons around remote sites. So we have identified some persons which will stay there for some duration. They will act as a security persons for that antenna, and they will inform us. Yes. The alarm facility is also available in case of emergency. We also designed the sentinel system for observatory building itself. So there various labs are there. So each lab is doing various different tasks. So that has to be very important thing to protect it as well. So we are again monitoring temperature, humidity, smoke and fire. Surveillance cameras are in place and panic alarms systems are also there. So it's functionality wise it is mostly same. So this is how the summary is. We have used a new technology for based on IoT. It is very simple and hardware design approach, fully integrated with sensors and cameras in a single model. Then instant communication with smartphone, iPad, laptop, server. Then free and open source softwares are used for this. It is very easy to learn and implement, and we have rapid application development approach we have used so that anyone can take on this. So these are the references. Okay, thank you. Any questions, ma'am?
These antennas, they are operated 24/7 all the time?
Yeah, 24/7. If we have 6 months working cycle, so in that 6 month working cycle, antennas are completely used for astronomical observations. After 6 months, we have 15-20 days downtime, in which we have to do regular maintenances and system checks and safety measures again for various systems, so that next 6 months can be operated without any failure. So
What have you observed by this?
these are the radio antennas.
How long it is working from 2002, right?
It is in since the world.
What are the results that you have?
We have searched some pulsars, some galaxies, newly formed galaxies are there, and some twin stars. It's some year back we have found a supernova burst. We have recorded it live actually. Yeah, and we have recorded it when it was bursting. So that supernova burst was recorded, and it was a major strike there. Yes. Sorry.
What sort of microcontrollers or some more specifications about that?
And that will require more time on this actually. So that will be in very deep. So that is sort of some electronics and all. But that's true. I haven't gone into various deep things. It is just a overview of this system. Yes.
You have how many persons working in that?
We have around 220 persons working there, from considering NCRA as well as GMRT.
Your basic question was why the antennas are arranged in Y. It's actually to observe very faint and far away sources. You have to look at the sources sky for long, because the sky was rotating, so you won't find the same source for very long time in the same place. So you need to keep tracking them. Like sun is rising, suppose you want to observe sun for 12 hours. You have to keep looking at the sun as it goes and sets in the west. Similarly, you need to track the sources. But interferometry is not a single telescope that is doing. It's a single disk, you can keep tracking like this. There are so many antennas there. By this, so many antennas of 45-meter diameter E, you are trying to recreate a 25-kilometer diameter radio antenna. So what you do is that you look at the same source which is rising, but all these antennas looking at the same thing. Whereas the source interferometry is a bit more complicated. It doesn't, the images are not formed at the focus. Unlike optical lens and mirror, images are not formed. Images are recreated by individual measurement of the center. Just trying to do kind of a Young's double slit experiment if you think. There are two antenna trying to track the source, trying to image. So what this source is actually seeing, the distance between two sleeves, distance between two antenna, is actually a projection of what it is really as seen from the source. Suppose the source is just rising, and there are two antenna 100 meters apart. It will not see 100 meters, it will see actually 0. It's just rising there. If the source is in the middle of the sky, it will see 100 meters. So as the source rises and sets, distance between antenna is actually different. So different distance is actually helping us because the distance between two antenna is kind of sampling the source sizes. For example, I am a Tamil. There are so many people, but I want to make friendship with only Tamil. It's kind of funny way of telling, but the distance between this antenna is related to what kind of angular size scale that the interferometer is going to see in the sky. So you want to actually have antennas 25 km spread all over, which is impractical. This is also a big region for that. So that way, if you have so many antennas east-west, 0, 100 meters, 75 meters, as the source rises and sets, let the redundancy, duplications happen. So you don't want to have the east-west area, all the antennas arranged in east-west, because the duplications happen 50 meters, 50 meters, 50 meters, 75 meters, 75 meters, 75 meters. So you don't want to have that. You rather want to be economy. So you spread them not exactly eastern, but slightly inclined. So that way, the distance between them are varying with time. So you are trying to recreate and fill with economically minimum number of antenna and maximum sampling of the 25 kilometers. That is the reason it is arranging that kind of thing. But that is the old technology. Now actually people are computer simulation trying to create what is the best possible way to distribute this antenna to create a huge synthetic antenna. So now we are actually thinking of spiral like structure. They are not Y-like thing. American VLA and GMRT is still work. American VLA is 3 railway tracks, straight line exactly. They pull the antenna in, they pull out the antenna. But GMRT is fixed on the ground, huge structure. Wherever land was available, there the antenna will put roughly Y, not exactly Y. Modern technique that is spiral arc, that is what it is.
Which is we call as non-thermal, because black body radiation is also called as thermal emission, so they name it like non-thermal emission. This actually comes from the fact that electron, when it comes in the influence of a magnetic field, it's guided around it, and as a result of that it emits radiation, and that has a very different properties with respect to the frequency, right? So Jyoti River was the, you can call it, first professional radio astronomer who did discovered radio emission, that is non-thermal, and he also did what we call professional astronomy in some sense, like he did research, published it in papers, and like that. He died in 2002, and at that time his ashes were actually distributed to some of the major observatories across the world, and if you happen to travel to GMRT, you would find that like, at a place at the observatory, a small box is kept which has Jyoti River stations. So if you visit GMRT, look out for this as well. So this was the takeoff of radio astronomy, and then after the war, especially like when a lot of dishes and resources were freed up, people started using them for radio astronomy. So now let's look at some of the key discoveries that has been made at these wavelengths. The first one, let's talk about quasars. So what are quasars? We have already looked at one of the image, like in which they are supermassive black hole, it's accreting matter, it produces huge amount of energy. So quasars are powered by such by this mechanism, and when radio astronomy took off, people made images of sky at radio wavelengths, but then they did not know immediately that what they are. When you see a blob, it has this much brightness, but what is it? We really do not know. So when they started making maps at slightly better resolution, then they were able to say, okay, this may be actually corresponding to this object at the optical wavelength, this star-like thing that I see in the sky. So they started taking optical spectra also, right? And optical spectra has different lines. And what happened with detection of these lines, that they were able to actually measure how far these objects are from us. And immediately they concluded that they are actually very distant objects. If you are familiar with the concept of redshift, some of the first objects were at redshift of 0.1, 0.2, 0.3. So these are really powerful sources which are extragalactic in nature. So this was the discovery of quasars. Today, more than 600,000 quasars are known in the universe. This is a field on its own. So these objects, or discovery of these objects, was enabled by radio astronomy. That's one thing. Next, as I was showing you this image of galaxy which was embedded in this big halo of neutral hydrogen. And neutral hydrogen, observations of neutral hydrogen is one of the main drivers at radio astronomy. And that happens because of this unique line at 21 centimeter line which is observable at radio wavelength. It's called 21 centimeter, I will explain. But in frequency it corresponds to 1420.405 megahertz, right? 1 gigahertz, 1.4 gigahertz. You find that to be easier to remember. So hydrogen atom has different energy levels, and transitions between them can be gives rise to Lyman series, Palmer series, Bastian series. Right? These are the lines that we see at UV, optical, infrared. Right? This is something that we are familiar with. But in the hydrogen atom, there is a certain phenomena through which if electrons and protons are interacting, then it splits the ground state of hydrogen atom into two different energy levels, right? And the energy of the state in which both electron and proton have parallel spins is actually higher compared to the state in which electrons and protons have anti-parallel spin. And between these two states, the separation corresponds to 21 centimeter in wavelength and 1420.4 megahertz in frequency. That's how this name of the transition comes from. And this is at radio wavelength. So it becomes a fantastic transition or a flow to look for neutral hydrogen in the universe. And neutral hydrogen is the most prominent or the most abundant element in the universe. We know that, right? So, and it's a basic fuel for anything that happens in the universe. So this is like then becomes or enables so many experiments that can only be carried out at radio astronomy. It presents a certain view of the universe which can only be obtained at radio wavelengths, right? So this is why I say that the 21 centimeter line is, or observations of neutral hydrogen in 21 centimeter line is one of the main drivers at radio astronomy. So, but how was this line discovered? So theoretically it was predicted by a Dutch astronomer Van der Helft, and while he was doing his PhD. This was an assignment given to him by his PhD supervisor Jan Oort, who was the director of Leiden Observatory, again in Netherlands at that time. So he theoretically predicted that this interaction of electrons and protons will lead to the split of the ground state of neutral hydrogen and will produce this radiation that should be detectable, right? So the moment it was predicted, there are several groups in USA, Netherlands, and Australia started setting up experiments. They started using actually dishes which were left over of the Second World War, because previously they were being used for aircraft navigation or tracking airplanes of enemy, but after war was over, there was no other use for it, so these engineers took over those dishes and started using them for radio astronomy. So three groups almost simultaneously confirmed the detection of this line from the gas in our galaxy, right? So theoretically predicted and experimentally confirmed. And as soon as that happened, like people started then setting up experiments to look for this gas in more and more distant galaxies. And again, like I just want to emphasize that this is an optical image of a group of galaxies. You see that there is nothing happening here, but if you look at the same group at neutral hydrogen line of 21 centimeter, you find that like they are actually interacting with each other. And this is what is going to shape the evolution of this group of galaxies. That's where it becomes important. So it has since then become an excellent flow for galaxy evolution to look at gas properties and their kinematics. Kinematics, because like we know that a spectral line, from spectral line we can also determine whether the gas is moving towards us or moving away from us, right? By using the phenomena of Doppler effect. So, and that is something which we cannot do with continuum emission. That's why spectral line plays such an important role. Again, like when I was describing to you that like there were these blobs of emission detected in the sky, but nobody knew what they are, where they are. But the moment they could take the optical spectra from emission lines, they could tell that these are really powerful sources which are far away from us. So spectral lines are very important. And then moving on from there, again, like theoretically, it was predicted by Alpert and Herman that from the Big Bang we must see a relic radiation which is called as cosmic microwave background radiation. That is the earliest or the oldest light in the universe that we can detect today. Nothing before that is detectable. And Penzias and Wilson again at Bell Labs, they were again carrying out a certain experiment which was related to telecommunication, but this time at a much higher frequency, like 20 gigahertz or something, or maybe even higher actually, much higher than that. And then they found that there is actually radiation which is present everywhere in the sky, right? And this led to the discovery of what we call as cosmic microwave background radiation. Was the confirmation, and for this they were awarded Nobel Prize in 1978. Okay, and this has actually set up a complete different branch of astronomy and cosmology, the detection of cosmic microwave background radiation. Then again in 60s there was a discovery of what we call pulsars. This was by Jocelyn Bell Burnell, who was doing PhD, and she was actually trying to this was also a serendipitous discovery. She was trying to detect some transit phenomena associated with stars, and they detected certain pulses in their observations. And at that time, they even tried to, or people tried to even say that this would be actually signal coming from aliens, some other civilizations, somewhere else in the universe. But eventually, it was confirmed that these are actually sources or astrophysical sources in our own galaxy, which were named pulsars. There is a model of pulsar outside this, and try to understand in more detail what they are. They are really unique objects. They are some most accurate clocks that we know in the universe, and using this one can actually test or carry out some of the most profound tests of Einstein's theory of general relativity. And so, and for both these tests, both the tests as well as the discovery were awarded Nobel. Nobel was in 1974 for the discovery, and then for carrying out the test of Einstein's general relativity in 1933, this was for Hull and Taylor. Right. So this is like key milestones in radio astronomy, key discoveries, but each one is actually starting a new branch in astronomy as a whole and discovering a totally different class of objects. Right. So how is imaging astronomy very different from imaging at any other wavelength? That's the question that we would like to understand, right? What is so different about it? I think astrophysically we are convinced that radio astronomy presents a very unique view of the universe, and we should really be taking that into account when we try to understand the universe. And if I'm giving a talk on optical astronomy, I will say the same thing about optical astronomy too. But since this lecture is about radio astronomy, I will sound a little bit biased towards radio astronomy. But it's essentially like putting together everything that we can. That's what multi-wavelength astronomy is about. So let's talk a little bit about the technology part of it. So there are two aspects of it when we do astronomy, which is to image objects in the sky. One is like we are talking about formation and processing of images, like how the signal is detected and converted into an image that we can understand. And then when we're talking about images, images can be of two types. One is that the spatial distribution, right, which is just telling that okay, this is bright here, then it faints here, then it looks circular or it's elliptical in nature. Like that's what is called spatial distribution. That what does it look like? But we can also do is that we can actually make its image at different frequencies, and that's what I will call a spectral composition. And this can again have two different aspects. One aspect is like if we are looking at it in a certain spectral line, then the signal will be received only at a certain frequency. So if you had an image like corresponding to that frequency, only the signal will peak, and that will show us like only atomic gas that is there in the galaxy, right? Another thing that we can weigh is that it's not spectral line, but I am taking or measuring the brightness of an object at different frequencies, right? And then if it's a black body, it will show a certain shape. If it's not a black body, it will show an opposite kind of dependence with respect to frequency. And that will tell me, in a very loose sense, that what physical process is giving rise to this emission. So what this object would be. For example, if you look at a star, it will show a black body type spectrum. If you look at an AGN or a quasar, it will show a non-thermal spectrum, right? So just by looking at that, measuring this brightness at different frequencies, we can tell like what is happening in this object or what this object could be, right? So these are the two things that we try to do in astronomy, like collect the data such that we get a spatial distribution and we also get a spectral composition of it, information at different frequencies. Now at optical wavelengths, astronomy is enabled by optical lenses, right? Lenses which are made of glass, because that's what will make the image on the CCD, and that's what we can collect straight away. But electromagnetic waves at radio wavelength do not really interact with matter the same way that they can have a lens made up of glass and make the images in the same way. We still do make lenses, but it is done with the help of computers. And mathematically, what we are doing is we do something called Fourier transforms, right? And this is something which is not very specific to radio astronomy. Like even if we take a lens or the lens in our eye when it is making an image, mathematically it is actually doing Fourier transform, right? But what happens that the lens made of glass at optical wavelengths is doing this mathematical operation naturally, right? We don't really have to do anything extra. But when we are talking about signal at radio wavelength, we have to create this lens with the help of computers. The way it is done that we take two dishes, as a signal from two dishes. If they are pointing at a certain source in the sky, it will generate a certain voltage, and then I will combine that voltage. Okay, and like this, I can have large number of dishes, and then I can make combine their signal in pairs. Like for example, if there are three dishes, 1 and 2, 2 and 3, 1 and 3, right? Like that, I can combine, and each one of them will give me a measurement, right? So I collect all such data, and then do what we call a Fourier transform of it with the help of the computer. And this idea of multiplying these voltages and then doing the Fourier transform is effectively equivalent to making a lens here, which actually gives me the image. Okay, so those images are then as real as what we would create using, say, lenses at optical wavelength. Very much the same, just the process is different. One important thing to also remember, especially if there are students who are doing bachelor's and master's science and they will be studying Fourier transforms, is that in this case when we are combining signals, we are not just combining the intensity of it, we are recording both amplitude and phase, right? So it's a vector quantity, and we combine them such that we don't lose the phase information, and that is very important. Because if we lose that, then it is not, we will not get then this thing will not, then the lens will fade, the lens will not be created. Okay, so that's the interesting part of. So when you are doing Fourier transform, try to understand it from this aspect. You will find it very, very interesting. So, let's take a step back and look at what does a single dish do. So this is a single dish, right? A parabolic reflector. If there is a source here, let's say there is a galaxy sitting here, and the radiation is coming from this. This is a plane wavefront. This is the radiation which is coming down on this dish, and then each point of this dish it will be reflected, and this is the focus where I can put a detector, and that's where a signal will be detected. It will be just a voltage here in this case, right? So what is this dish doing? Is that what is the property of a wavefront? Wavefront is that like each point in this is in phase with each other, right? That's the property of a wavefront. You are not following it completely, you can go back and read your optics books and you find that this is a very simple phenomena. But what I'm trying to tell you here is that like as the light is reflected from each point here, they are combined in phase, which means that the distance from this point to this point, this point to this point is the same actually. So they are adding in phase with each other. Like if there were 10 cycles of this wave here, there were also 10 cycles here. This is what it means, combining in phase. If they are off a little bit by phase, then this will not happen, right? Then this signal strength will go down. That's why we put detector at the focus. That's what this parabolic reflector is doing. And then what this enables is that this enables me to actually look at a certain part of the sky and tell me what is the brightness at that point in the sky. And why this does? Because it actually can collect signal only from a certain part of the sky. That's the property of a dish. So if a dish is like this, it has a certain power pattern, which means that it can only detect signal from there, right? If there is that bulb there, that certain thing will not contribute to signal here in dish. So whatever I detect at the end of the voltage, as a voltage, I can say that it's coming from here in this direction, and this is what, how strong it is, right? And like this you can do for the entire, let's say, sky, and then you can like, oh, there's a brighter source here, there are fainter sources there are some other fainter sources there, right? Like that you can start mapping the sky with a certain resolution. Resolution is important because the larger the dish, the better the resolution, which means that better is my ability to resolve two nearby objects. If I have a very small dish, I will not be able to tell whether these two are actually two separate objects. It will just appear as one big block, but I can then have a larger dish which will have a better resolution. Then I can tell, oh no, this is not one very bright block, this is actually two slightly fainter blocks, right? Like that. So this is why we want to build bigger and bigger dishes, because bigger dishes actually give you more sensitivity because you are collecting more light, okay? And also it gives you what is called the directivity, which means that you know that from which direction the radiation is coming, and that also tells you, like, you know, that what this object looks like, okay? So that's why we want to be bigger and bigger telescopes. So this is just a summary of ICET, but if you look at giant meter radio telescope, which is made up of dishes of 45 meters, it has 30 dishes. It has many dishes because we combine signals, because we want to create this lens which will make an image, right? This is the idea, that's why we have more dishes. But this 45-meter dish, actually, if I just take the signal from a one dish, it will give me a resolution of 0.3 degrees at 1.4 gigahertz. This is the frequency of 21 centimeter line. Now I will tell you what does 0.3 degrees mean actually, right? So half a degree, that's the angular size of sun or moon. You look at it in the sky, and if we look at the nearest star forming region in the sky, this is Orion Nebula. Again, all those who do amateur astronomy must have seen Orion Nebula. Orion constellation, I'm sure everybody has seen. This is one constellation which we can see despite living in the cities. And so this is again of the similar size, and you will find that like there is so much structure here. There are stars forming, there are dust lanes here, and there are parts where supernova is taking place. And if my telescope can just give me a measurement over this entire region, it just tells me, give me one number for that. That number does not mean physically anything, right? Because the properties of the physical processes that are taking place where the star is dying are very different from the region where stars are forming, or the region where there is lot of dust and stars will form in future. So I must have an instrument which gives me a resolution which allows me to separate out these regions, right? So 0.3 degrees is not a good resolution at all. So you have a feel for it now, and you can work out these numbers very easily. This is very easy, like lambda by d is the wavelength and d is the size of the aperture. Right? That's just dividing two numbers. Second, third standard student can do this. It's not big deal, right? So again, this is the so what I will do is I will can make an image by pointing like telescopes like this, right? Which is what we were talking about, and map this. If I have a good resolution, and I can do my astronomy. But 45 meters is not good enough, 0.3 degrees, and you will tell me that, okay, if you want to get better angular resolution sensitivity, you were telling me that make bigger dishes, right? But how big we can make, right? There is a practical and mechanical limitation to making larger dishes as well. And angular size of Orion Nebula is 1 degree, as I was saying, right? So 0.3 degrees, this is, right? So just 3 measurements across the entire Orion Nebula. It's useless observation, you can tell. So indeed, people have tried to make bigger dishes. Like this is 64-meter diameter Parkes telescope in Australia. It was it has been around since 50s onwards. And then Green Belt telescope. This is the largest steerable dish. This is a diameter of 100 meter. 100 meters is huge actually, right? And it's very heavy too. More than that, it's very difficult to make steerable dishes, which will also retain their shape and they can be steered because the gravity becomes enormous on the burden on the structure. So people have tried to build what we call as telescopes which are not really steerable, and they take advantage of the natural geographical formation on the ground. For example, this is in Puerto Rico, it's called Arecibo telescope. 300 meter in diameter, it's built in a crater, right? So naturally a shape where you put panels of steel, so it gives you a radio dish, and then you make a 300 meter size dish. It cannot steer whatever comes passes over the telescope, you just detect that, and that's how you do. And now China is in the process of commissioning 500-meter diameter such telescope. It will be called FAST, 500-meter aperture spherical telescope. It's already started doing some observations. So you can see that like there's a limit to what we can do with just by making large dishes like 40 meter, 50 meter, 100 meter, and that's it, right? And if you make a non-steerable dish, you can only see certain parts of the sky, so it does not really become very lucrative. Also, so what we do is called radio interferometry. So that's the word we use for the technique that I was talking about, that you take these different dishes and you actually combine signals in phase, right? Why do you combine in phase? Why do you take amplitude and phase? Because that's what this dish that I was describing to you, right, is doing at the focus, right? So I take signal from these dishes. So in case of GMRT, 45-meter dishes spread over an area of 25 kilometers, right? I take signal from each one of them, combine them in pairs, taking amplitudes and phase both into account. It's actually equivalent to an operation which is actually generating a dish of the size of 25 kilometers in diameter, right? So this technique is called radio interferometry, and also what we call as aperture synthesis. Because using this technique we have synthesized, right? We have not built, we have synthesized an aperture of the size 25 kilometer just by using dishes of 45 meter, but spreading them around an area of 25 kilometer and combining the signals appropriately by taking amplitude and phase into account. And that's called the technique of radio interferometry. So that's what we use at radio astronomy nowadays, because that gives us the resolution. So instead of single dish, use a number of smaller antennas and add signals in pair electronically. Add is used loosely here, right? It's not, you are not really doing plus addition. Okay, and for this, developing this technique or implementing it at the radio wavelengths, because ideas to some extent were already there from experiments such as Michelson's interferometer. If you have heard about some of these experiments, which were done by Michelson, and he was awarded Nobel Prize in 1900 and so for developing those techniques at optical wavelength. Martin Ryle, was a radio astronomer, was awarded Nobel Prize in 1974 for demonstrating and implementing this technique at radio wavelength. Right. So this is such a novel and an exciting subject to really understand, both from optical wavelengths aspects and also from like how do you interferometer optical wavelengths and also radio wavelengths. And there's a lot of nice literature that is available. You can start reading it while you are doing your 11th, 12th, or undergraduate degree and postgraduate, and you will find that like entire mathematics, Fourier transforms, all sets of optic experiment, Young's double slit experiment, or when you see diffraction from a single slit, all this is like just comes together and enlightens you towards understanding radio interferometry. So this is just an image of GMRT. 30 dishes of 45 meter diameter spread over 25 kilometer. Must try and visit if you haven't already done so. And resolution and sensitivity are determined by how array configuration. Array configuration is refers to how these dishes are distributed on the plane. Further you distribute them, better resolution you will get, right? Because it will synthesize a dish of a much larger aperture. There are no other radio interferometers also across the world, like very large array. It's the 27 dishes of 25 meter diameter. The difference with respect to GMRT is that in this case, dishes are actually put on rail tracks. Okay, and what this allows them to do is to actually move these dishes close by if they want to synthesize a dish of smaller aperture, because then they can look at large scale distribution of objects in the sky. And if they want to actually look at final details, they want to synthesize a much larger dish, they move these dishes apart. Right? So using the same, in case of GMRT, the dishes are fixed. So that's the difference between the two. And now a little bit about like why all this is becoming more relevant and more exciting. And all of you already know about it. This is because like the astronomy community is now working towards the world's largest radio telescope, what is called as 12 kilometer array. And this is the largest radio telescope that has ever been built, and it is so complex and so huge and requires so much resources that it is not possible for a single country or a couple of countries to build. two different sites. One site is in South Africa, Southern Africa, I should say, and another one is in Western Australia. Now you know I'm quite certain that why these are being built there and not, let's say, in India, and that's because like we want to put places where there is as less disturbance as possible from mobile phones and all the technology that interferes with radio astronomy, right? So these are the sites which have like minimal human population, okay, and there are very few places on the